So this training video covers the statistical method, specifically how it can and is used to estimate QMED. So just before we begin the presentation, it's important to highlight what prior knowledge is useful to understand the training material. Participants should have a general understanding of the flood estimation handbook and a familiarity with the data set underlying this. More information on both these topics can be found in our two training videos, Introduction to FEH and FEH datasets, both of which are available on our website. So what's this presentation going to cover? So firstly, we'll start with an overview of the statistical method as a whole, looking at what it is seeking to determine. We'll then go on to cover a key facet of the method, which is the estimation of QMED, your median annual flood. Finally, we'll finish with a quick demonstration of the software and the tools used to estimate QMED. So as you will have seen, the FEH methods are formed by two distinct approaches. You have the rainfall runoff method and the statistical method. The statistical method is applied in the software WINFAP, and it uses data sets from the FEH web service to derive information for your target catchment. And unlike the rainfall runoff method, it also makes use of the NRFA, the National River Flow Archive's peak flows dataset, which includes gauging station data from across the UK. So firstly, focusing on WINFAP, the basis for the methods used by the software are from the original FEH handbook methods released in 1999. However, since the release of the handbook, there have been a number of updates. For instance, with the release of WINFAP 3 in 2009, the findings of DEFRA-funded research carried out in 2008 were incorporated into the software. This included allowing you to use one donor station to refine your QMED estimate and an update to the similarity equation used to derive pooling groups for growth curve estimation. The second was in 2016 with the release of WINFAP version 4. Some of the main improvements to the software were ergonomic to make the software more user-friendly. However, there were also some updates on the technical side. QMED could now be estimated using multiple donors rather than a single donor, which could be applied in WINFAP version 3. You could also use local data for growth curve estimation. Just to note, in 2020, there are due to be some further updates to WINFAP, incorporating some of the small catchments research being undertaken by the EA and DEFRA. This should hopefully make the software more applicable in smaller catchments. So looking at the statistical method, what is it and what is it looking to estimate? So in explaining this, I think the best place to start is with a gauge site. In this context, a gauge site will be a gauging station which has a flow record. Now, one of the key data sets within a flow record will be an AMAC series. This is a record of the annual maximum event, so the maximum recorded flow for each year of the record. So here's an example in this bar chart here. There's a maximum flow recorded for each hydrological year. Now, what you can do, if you have an AMAX record that covers a significant length of time, you can plot the magnitude of events against their expected frequency of occurrence, or their return period in this case. Having plotted the points, you can then fit a distribution through these points, and this distribution can form what's called a flood frequency curve, which can be used to predict the peak flow for a given return period. Now, what the statistical method seeks to do is estimate this flood frequency curve, but not only for gauge sites, but also for ungauged sites. So how does it do this? There are two main things it looks to estimate: an index flood and a growth curve. So the index flood typically used is the QMED, which is the median annual maximum flood. Now, if you have an AMAC series, it's just the median of all those events. You then use a growth curve, which is used to scale your index flood. So your median annual flood is typically proportional to a 2-year return period event. But what if we want to estimate to a 100-year event? What we would do is look at our growth curve, which, say, for the 100-year event had a multiplication factor of 3. We would multiply our index flood by 3, and that would give us an estimate of flow for our 100-year event, which would be around 15 in this case. Now, for ungauged sites, we don't have an AMAC series to derive our QMED. Therefore, we need to use an alternative method. Namely, we can use the FEH web service catchment descriptors we have for our ungauged catchment. We also can't base our growth curve on an AMAC series or any gauge data. We therefore need an alternative method here also. So here we'll look at growth curves in similar catchments which are gauged. Now, in this presentation, we're going to be focusing on QMED estimation, so we won't be looking at the growth curve in much detail. That will be covered in a separate video. So this slide lists the techniques available within the statistical method to estimate QMED. So if your site is gauged and you have a long, reliable record, you can move straight ahead with either estimating your QMED using your annual maximal series or your what's called your peaks over threshold series, which I'll describe in more detail later. If you have some gauge data, but it may not be suitable for high flows, there is another method which is called the catchment descriptor and flow variability method. So that will use your catchment descriptors for your catchment, but also allow you to incorporate whatever gauge data you do have available. What about for ungauged sites? Well, the first port of call is really the catchment descriptor method, which is an equation, which will be detailed in the next slide. But that can be refined using donor transfer, and it can also be refined if you have a measurement of your bank fall width, which is the catchment descriptor and channel dimension method. So starting with ungauged methods, as ungauged catchments tend to be far more numerous. So firstly, we'll start with the catchment descriptor equation. So this has a factorial standard error of 1.43, and that's based on looking at its accuracy across 602 gauge sites and comparing their observed QMED values to what the catchment descriptor equation estimates. As we'll see when we incorporate more local data, for example, when we apply the donor transfer method, that factorial standard error will come down close to 1. So the catchment descriptor approach is based on an equation. The equation you can see in the center of your screen. Now, this equation looks quite complicated, as you've got a lot of long numbers with multiple decimal places, you've got exponents, but really what you need to be thinking about here is what affects magnitude of flows through a catchment. So clearly, area does. Larger catchments capture more runoff, leading to higher river flow. Secondly, we have SAR. Now, the SAR stands for the standard average annual rainfall. So if our catchment is wetter, the QMED also goes up. Thirdly, we have a term called FAL. This stands for flood attenuation by reservoirs and lakes. If we have more storage in our catchment, that will attenuate peak flows, so you'll get a lower QMED. Finally, we have BFI host. This stands for base flow index, and the host refers to the soil data set which is used in this case. And that's basically a measure of permeability. Higher BFI host values are related to more permeable catchments. More permeable catchments have higher base flows, which lessens the peak flows we see in rivers. So our QMED estimate, or our annual maximum flood, is going to be larger if we have a catchment that's, well, large, wet, has few reservoirs and lakes to attenuate peak flows, and is impermeable. In all cases, really, the catchment descriptor equation should be thought of as a first port of call, as I've already mentioned, which should be refined using real-world local data if it is available and if it is suitable. The main method used to improve the catchment descriptor equation estimate is donor transfer. So what WINFAP will do, it will search for nearby gauging stations which can be used as donor stations to adjust your initial catchment descriptor estimate. As you can see, using this method, we see a fall in the factorial standard error, which suggests increased accuracy, and that's on the same data set as was used for the catchment descriptor equation. So how does donor transfer work? So basically, it searches for nearby donor stations and allows comparison between the QMED catchment descriptor estimate and the observed QMED. From this analysis, we can infer whether there is a systematic under or overestimation by the catchment descriptor equation in a particular area and adjust our QMED estimate to account for this. Now in WINFAP 3, only one donor station can be used, and the following equation would be applied. This basically takes into account the ratio of the observed QMED at our donor site to what would be estimated by the catchment descriptor equation at our donor site, and then multiplies what's observed at our ungauged site using the catchment descriptor equation. So if our observed QMED at our donor site is significantly higher, we're going to get a ratio above 1, which accounts for the fact that we think the catchment descriptor equation is underestimating QMED in this area. And we get a final adjusted QMED value there. Now there's also another term you can see there, ASG, which basically accounts for the distance your donor station is, the distance between your donor site and your ungauged site. The greater that distance, the less influence your donor station is going to have. Now this is useful, but relying on one station to represent a trend across an area is fraught with uncertainty. Therefore, WINFAP 4 allows you to use up to 6 donors. You don't just use 6 donors off the bat. Donors should have similar catchment characteristics to your ungauged site. Most importantly, you're really looking at descriptors BFI host, SAR, and FAL. Area is also important, but less important if multiple donors are being used. And again, the effect of donor stations is determined by their distance from the target site and also the residuals. So that's the difference between what's estimated by the catchment descriptor equation and what's observed at those sites. So if you've got a donor station that's very close and there's a big difference between the observed QMED and the catchment descriptor QMED for that donor, then it's likely to have a big impact on your ungauged catchment estimate. There is a third approach that can be used on ungauged sites as well. So if you have a measure of bankfall width, WINFAP will allow this data to be inputted and will adjust the catchment descriptor estimate accordingly. Again, it is using locally available data to refine your estimate, but the advice is to use with caution as it has been developed using a far smaller data set than the descriptor equation and donor transfer method. As you can see, only 73 stations there in comparison to 602. There is a small reduction in factorial standard error, but again, the advice is really to use this with caution. So what about gauge sites? So if you have a record of over 13 years, you will most likely use the annual maxima flood series and take the median of that flood series. You also need to consider whether the gauging station is suitable. So you might have a record that's over 13 years, but if there's significant bypassing upstream of the site, it may not be appropriate. If there's abstractions upstream of the site, that may also be a cause for concern. The NRFA peak flows dataset does give you information on QMED suitability, so that's worth looking at before using the annual maxima QMED estimate. Now, if your station record is less than 13 years, you want to use an alternative method called peaks over threshold. Now, the peaks over threshold series contains all peak flows that are greater than a given threshold value. Now, generally, the threshold is set to include an average of 5 events per year. Now, if your record is below 2 years, you may just want to treat it as an ungauged site and estimate QMED using the methods we just went through. There is potential to extend the subject site's annual maxima or peaks over threshold record by correlating with a nearby long record site, but this is rarely appropriate. Now, there is another method which can be used if you have, for instance, gauge data, but it may not be suitable for high flows. So you may have low flows data over a more limited period. You can use that to restrain your catchment descriptor estimate. And what you need there is an estimate of your Q5 and your Q10 flow. That's the flow exceeded 5% of the time and the flow exceeded 10% of the time. So what method should you really use to estimate QMED? I think if your site is gauged and you, in an ideal world, you use the annual maxima series or the peaks over threshold method, depending on the length of your record. If your site is ungauged, the catchment descriptor equation should just be thought of as a first port of call. You should always look to improve it using local data. And in most cases, that will be using donor adjustment. So just a quick note on urbanization. You may have noticed that the catchment descriptor equation, which ungauged sites are based on, the QMED estimate at ungauged sites is based on, doesn't include a term for urbanization. Therefore, we need to adjust this. And the way we do this is using an urban adjustment factor. So we multiply our QMED rural value by a UAF. The UAF will be 1 if our catchment is completely rural, so there'll be no impact by urbanization. The greater urbanization is, the higher that value goes above 1. So how is the UAF derived? So it's based on this term here, which is the percentage runoff urban adjustment factor. Basically, the increase in runoff volume that occurs as a consequence of urbanization. And it's related via these equations here, which again look a bit confusing, but taking all this into account, the UAF is going to be higher if you have a large urban area with a high proportion of impervious surfaces, which quickly transfer rainfall into direct runoff. It's also going to be higher if the underlying natural ground is permeable. That's why we can see this BFI host term. As the impact of replacing permeable ground with impermeable surfaces is greater than, say, replacing an impermeable substrate like clay with urban surfaces. So I've loaded up WINFAP. So we will load in our catchment now. So file, new project, file, import catchment. Catchment is here, it is ungauged. So we'll right click, pooled and QMED analysis, leave those terms as default for now. And the software has loaded up a pooling group, which is used for growth curve estimation. Here we're going to be focusing on QMED estimation. So we want to click Edit QMED Method. Now, by default, it's estimated a rural QMED based on the catchment descriptor equation of 19.372. We can attempt to adjust this estimate. For instance, say if we have a measurement of bankfall width at our site, we could put a value of, let's say it's 10, and then the software would refine that catchment descriptor estimate and bring it down to 17.767. We could also, if we had some gauge data, which maybe gives us an estimate of our Q5 and Q10 flows of, let's say, 1 QMEC and half a QMEC. Now, the base flow index is a measure, again, of how much base flow there is. I think for this catchment, the BFI host is around 0.5, so we'll assume it to be around that. And again, that's reducing our QMED. So based on the gauging data we have available, the software is suggesting that the catchment descriptor equation is slightly overestimating our QMED value. So those two methods are rarely used. In most cases, you're going to be applying donor adjustment. And that brings up this screen here. So the 6 closest stations suitable for QMED are selected by default. And the first thing you're going to want to look at is the relationship between the QMED derived using the catchment descriptor equation here against what is observed at these sites. So in this case, we can see quite a clear systematic overestimation by the catchment descriptor equation of the observed QMED. The QMED estimated here is 35 by the catchment descriptor equation, where it's sort of 21, and then we see this pattern continue as we move down the donor group. We don't want to just use these stations straight away. We need to check that they are similar to our target site. So our target site has a SAR value of 852, BFI host of 0.53, and a file value of 0.989. We can see that these stations are reasonably well matched when we compare the catchment descriptors. There may be a case to reject 67005 just because its SAR value is quite a lot higher than our target site. So we'll remove that. Again, we don't want to move straight ahead and apply these 5 stations. It's worth looking at the station outside of the default 6 initially selected. So we've got a station here. I've looked at this donor group previously, and this station looks appropriate. You've got similar SAR value to the target site, similar BFI host, and similar file. So we'll use these 6 stations. Before we apply them straight away, we want to de-urbanize their QMED observed value. If you don't do this and then apply the UAF later on, the urban adjustment factor, it double counts for urbanization. So it overestimates the impact of urbanization on your QMED. So what's happened when we've applied these 6 stations is you can see the catchment descriptor estimate has been reduced to 14.682 to account for the fact that we believe the catchment descriptor equation is overestimating QMED in this area. So we have a final rural QMED estimate of 14.682, but we want to adjust this for urbanization. The UAF for this catchment is 1.125, so that is multiplied through by that rural value, giving us an urbanized QMED value of 16.521, which will be used to scale the growth curve. So that is the end of this training video. I hope you found it useful. More information on the statistical method and WINFAP specifically can be found on our website.